Hey everyone, I'm Morgan Willis, Principal Cloud Technologist at AWS, and I want to welcome you to this course. In this course, you will learn the key concepts behind cloud computing and explore AWS services using real life examples covering compute, networking, storage, databases, security, and more. This course is intended for people working in IT or IT related fields who have a general knowledge of IT topics but have yet to learn much about the AWS cloud. To kick off the course, we will cover the basics of what the cloud is, the benefits of the cloud, the AWS global infrastructure, and identity and access management. This will give you a solid foundation for learning the rest of the more technical topics contained in the course. Then we will focus on computing, and for this topic, we will dig into the services Amazon Elastic Compute Cloud, AWS container services like Amazon Elastic Container Service, and serverless compute options like AWS Lambda. Then we will discuss networking in AWS using services like Amazon Virtual Private Cloud and other networking technologies used for creating, securing, and connecting to your own private network in AWS. For storage, we'll explore how and when to use Amazon S3, Amazon Elastic Block Store, and others. For databases, we will cover many use cases around the different database services AWS has to offer, but with a special focus on Amazon Relational Database Service and Amazon DynamoDB. Then finally, we will discuss monitoring and scaling your application. For that, we'll use Amazon CloudWatch and Amazon EC2 auto scaling alongside Elastic Load Balancing. We aren't going to focus on theory alone in this course. Instead, we will use a hands-on example through a cloud-based application that will build over the duration of the course piece by piece. The app we will build is an employee directory application that stores images and information about fictional employees in a company. This course includes written segments we refer to as readings or notes to reinforce ideas, dive deeper into topics, as well as provide background information on concepts we did not cover in the videos. Because of this, I highly suggest that you take the time to complete all of the readings to get the full benefit of the course. So, again, welcome. And as we say at Amazon, work hard, have fun, and make history. More on that later.
Hey y'all, I'm
Hey everyone, my name is Morgan Willis. I'm a principal cloud technologist with AWS. What that means is I essentially build things, learn AWS, and then I get to share my knowledge with you all. I had a career in software development before I started working in training and certification here at AWS. I really love technology and have been in the field for over 10 years in roles from technical support to database administration to web application development. And while it's true that I do love technology, I also have a regular life outside of work where I like to hike in the beautiful sun, rain, sleet, or snow. I also like to ski and really enjoy just about any outdoor activity all seasons of the year. I'm looking forward to helping you navigate the world of AWS over the coming lessons. And this here is Meowsy. He's my trusted sidekick. He spends time with me while I type away on my computer, and I think he's picked up a thing or two over the years. His knowledge of AWS at this point is pretty great for a cat. I think I can even hear him sneaking on my computer in the middle of the night to build his own solutions on AWS. I have a feeling his knowledge will come in handy for this course. More on that later.
Hey y'all, I'm Seth. I'm a cloud technologist with AWS, and I've been working with the AWS cloud for close to 15 years. Like Morgan, I have spent most of that time learning, building, and sharing my knowledge with customers like yourself. In addition to my experience with AWS, I have worked in a variety of industries, and I've been on both the data center and the cloud side of infrastructures. Outside of my life in tech, I mostly enjoy spending time with friends, which primarily includes my 4-year-old wonder dog named Fluffy. Speaking of Fluffy, Sometimes I think she knows more about AWS than she lets on. Every once in a while, I notice her drawing AWS architectures in a journal, and I wonder where she learned all of this. She can't bring me the ball back when we play fetch, but she always wags her tail when I mention cloud computing. I think Fluffy has something to say about cloud computing, so stay tuned for some of her helpful tips and tricks. For our employee directory application, we'll be using photos of each of our employees. If we have only one copy of those photos and don't want to lose them, we have to store them somewhere safe. Currently, the only copy of these photos are saved on my laptop. But if my laptop breaks, what happens? No more photos. I want to make sure this doesn't happen, so I'm going to upload the photos to AWS to ensure that the copies exist even if my laptop is destroyed. This also allows me to access my photos from anywhere: my home, my phone, a plane, on a train, everywhere. When I store these photos in an AWS service, I'm storing it in a data center somewhere, on servers inside that data center. But if a natural disaster happens, such as an alien coming down from space and destroying a data center, then what do we do? Luckily, AWS has planned for this event and many others, including natural disasters and other unavoidable alien accidents. The way they plan for it is through redundancy. AWS has clusters of data centers around the world. So here, AWS would have a second data center connected to the first through redundant high speed and low latency links. That way, if the first data center goes down, the second data center is still up and running. This cluster of data centers is called an availability zone, or AZ. An AZ consists of one or more data centers with redundant power, networking, and connectivity. Unfortunately, sometimes natural disasters like hurricanes or other disasters might also extend to impacting an entire AZ, but AWS has planned for that too, again using redundancy. Like data centers, AWS also clusters AZs together and also connects them with redundant high speed and low latency links. A cluster of AZs is simply called a region. In AWS, you You get to choose the location of your resources by not only picking an AZ, but also choosing a region. Regions are generally named by location so you can easily tell where they are. For example, I could put our employee photos in a region in Northern Virginia called the Northern Virginia region. So, knowing there are many AWS regions around the world, how do you choose an AWS region? As a basic rule, there are four aspects you need to consider when deciding which AWS region to use: compliance, latency, price, and service availability. Let's start with compliance. Before any other factors, you must first look at your compliance requirements. You might find that your application, company, or country that you live in requires you to handle your data and IT resources in a certain way. Do you have a requirement that your data must live in the UK boundaries? Then you should choose the London region. Full stop. None of the rest of the factors matter. Or if you operate in Canada, then you may be required to run inside the Canada Central region. But if you don't have a compliance or regulatory control dictating your region, then you can look at other factors. For example, our employee photos are not restricted by regulations, so I can continue looking at the next factor, which is latency. Latency is all about how close your IT resources are to your user base. If I want every employee around the world to be able to view the employee photos quickly, then I should place the infrastructure that hosts those photos close to my employees. We are all bound by the speed of light. Applied to your business, that means that if your users live in Oregon, then it makes sense to run your application in the Oregon region. You could run it in the Brazil region, but the latency from Oregon to Brazil might impact your users and create a slower load time. But maybe I really want to run my application or store my employee photos in Brazil. One problem I might run into is the pricing, which is the next factor we'll talk about. The pricing can vary from region to region, so it may be that some regions, like the Sao Paulo region, are more expensive than others due to different tax structures. So even if I wanted to store my employee photos in Brazil, it might not make sense from the latency perspective or the pricing perspective. And then finally, the fourth factor you'll want to consider is the services you want to use. Often, when we create new services or features in AWS, we don't roll those services to every region we have right away. Meaning, if you want to begin using a new service on day one after it launches, then you'll want to make sure it operates in the region that you're looking at running your infrastructure in. To recap, regions, availability zones, and data centers exist in a redundant, nested sort of way. There are data centers inside of availability zones and availability zones inside of regions. And how do you choose a region? By looking at compliance, latency, pricing, and service availability. Those are the basics, but it isn't the end of the story when it comes to AWS global infrastructure. We also have the Global Edge Network, which consists of edge locations and regional edge caches. Edge locations and regional edge caches are used to cache content closer to end users, thus reducing latency. Consider this scenario. You are a company hosting a website to your users all over the world. Even though your website is being downloaded from all over, it's hosted out of an AWS region in North America, say Ohio. Without caching, every user would need to send a request to the Ohio region where the data is downloaded, and then the data would be returned to the user and rendered in their browser. If the user is located in the USA or a nearby country, there may not be much latency in this process. However, if a user is coming from a place that is located far from the Ohio region, then latency will be greater. Latency is a big hurdle for many use cases, including web applications. So, to reduce this latency, you could use the edge locations to cache frequently accessed content. When you cache content at an edge location, a copy is hosted across the edge locations around the world. That way, when a user goes to retrieve that information, it will come from the closest edge location, which will greatly reduce the latency for that user. You can use services like Amazon CloudFront to cache content using the edge locations. When you own the infrastructure, it's easy to understand how you interact with it because you can see it, touch it, and work with it on every level. If I have a server that I've stood up in my closet, interacting with that server is easy because it's mine. I can touch it. When I remove the ability for me to touch and see something, like when the infrastructure becomes virtual, the way that I work with that infrastructure has to change a bit. Instead of physically managing my infrastructure, now I logically manage it through the AWS Application Program Interface, or API. So now, when I create, delete, or change any AWS resource, whether it's a virtual server or a storage system for employee photos, I use API calls to AWS to do that. You can make these API calls in several ways, but the three main ways we're going to talk about in AWS are the AWS Management Console, the AWS Command Line Interface, and the AWS Software Development Kits, or SDKs. When people are first getting started with AWS, they typically use the AWS Management Console. This is a web based method that you log into from your browser. The great thing about the console is that you can point and click. By simply clicking and following prompts, you can get started with some of these services without any previous knowledge of the service. With the console, there's no need to worry about scripting or finding the proper syntax. When you log into the console, the landing page will show you services you've recently worked with, but you can also choose to view all of the possible services organized into relevant categories such as compute, database, storage, and more. If I change the region to Paris, You're making requests to eus3.console.aws.amazon.com or the Paris region's web console. After you work with the console for a while, you may want to move away from the manual creation of resources. For example, in the console, you have to go through multiple screens to set configurations to create a virtual machine. And if I wanted to create a second virtual machine, I would need to go through that process all over again. While this is helpful, it also leaves room for human error. I could easily miss a checkbox or misspell something, or even skip important settings by accident. So, when you get more familiar with AWS, or if you're working in a production environment that requires a degree of risk management, you should move to a tool that enables you to script or program these API calls. One of these tools is called the AWS Command Line Interface, or CLI. You can use this tool in a couple of ways. One is to download the tool and then use the terminal on your machine to create and configure AWS services. Another is to access the CLI through the use of AWS Cloud Shell, which can be done through the console. With both of these options, instead of having a GUI like the console to interact with, you run create commands using a defined AWS syntax. For example, if I wanted to launch a virtual machine with the CLI through Cloud Shell, I first use this quick shortcut to open a session. Once my session is started, I type in AWS, which is how we know we interact with the API. Then type in the service. In this case, it's EC2, the service that allows us to create and manage virtual machines, which we'll learn about later. And then the command that we want to perform in that service, and any other configurations we want to set. One command versus multiple screens you have to click through in the console can help reduce accidental human errors. But that also means you have to work with defined syntax and get that syntax correct in order for your command to run successfully. So there is some upfront cost in just understanding how to form commands, but after a while, you can begin to script these commands out, making them repeatable, which can greatly improve efficiency in the long run. The other tool that allows you to interact with the AWS API programmatically is the AWS Software Development Kits, or SDKs. SDKs are created and maintained by AWS for the most popular programming languages such as Python, Java, Node.js, .NET, Ruby, and more. This comes in handy when you want to integrate your application source code with AWS services. For example, our employee directory application runs using Python and Flask. If I wanted to store all of the employee photos, including pictures of employees, in an AWS storage service, I could use the Python SDK to write code to interact with that AWS storage service. The ability of managing AWS services from a place where you can run source code with conditions, loops, arrays, lists, and other programming elements provides a lot of power and creativity. All right, that wraps this video up. To recap, you have three main options to connect with AWS: the console, the CLI, and the SDKs. In this course, we'll mainly be using the console to interact with the services, but feel free to challenge yourself by using the CLI if you're a bit more advanced.
In order to begin using AWS effectively, it's important to understand how security works in the cloud. You already know that by using AWS, you won't be managing every single aspect of hosting your solutions. You'll rely on AWS to manage portions of your workloads for you, taking care of that undifferentiated heavy lifting, like running the day to day operations of the data centers, and managing the various virtualization techniques employed to keep your AWS account isolated from, say, my AWS account. So the question is, who is ultimately responsible for security in AWS? Is it A, you, the customer, or B, AWS? The answer? Well, the correct answer is yes. Both you and AWS are responsible for securing your AWS environment. Let's explore this concept. AWS follows something called the shared responsibility model. We don't view solutions built on AWS as one singular thing to be secured. We see it as a collection of parts that build on each other. AWS is responsible for the security of some aspects. The others, you are responsible for their security. Together with both you and AWS following best practices, you have an environment that you can trust. Let's take a look at the shared responsibility model diagram. You can see we have the responsibility of security broken into two groupings, you and AWS each being responsible for different components. We describe AWS as being responsible for security of the cloud. For example, one piece of the puzzle for AWS is the AWS global infrastructure. And when I say global infrastructure, I mean the physical infrastructure that the cloud is running on. This is iron and concrete, buildings with fences protected by security guards and various other security measures. It also includes the AWS global backbone, or the private fiber cables that connect each AWS region to each other. Managing the security of these pieces is all on AWS. You don't need to worry about that as far as security goes. Then there is the infrastructure and various software components that run AWS services. This includes compute, databases, storage, and networking. AWS is responsible for securing these services from the host operating system up through the virtualization layer. For example, let's say you want to host some virtual machines or VMs on the cloud. We primarily use the service Amazon EC2 for this use case. When you create a VM using EC2, AWS manages the physical host the VM is placed on, as well as everything through the hypervisor level. If the host operating system or the hypervisor needs to be patched or updated, that is the responsibility of AWS. This is good news for you as the customer, as it greatly reduces the operational overhead in running a scalable and elastic solution leveraging virtualization. We will talk more about EC2 and elastic solutions in upcoming lessons. For now, let's get back to the security aspect. So, if AWS manages the underlying hardware up through the virtualization layer, then what are you responsible for? Well, you are responsible for security in the cloud. Similar to how a construction company builds a building, and it's on them to make sure that the building itself is stable and secure. Then you can rent out an apartment in that building. It's up to you to lock the door to your apartment. Security of the building and security in the building are two different elements. For security in the cloud, the base layer is secured by AWS. It's up to you to lock the door. So, for our EC2 example, you are responsible for tasks like patching the operating systems of your VMs, encrypting data in transit and at rest, configuring firewalls, and controlling who has access to these resources and how much access they have. The main thing to understand is that you own your data in AWS. You are ultimately responsible for ensuring that your data is encrypted, secure, and has proper access controls in place. In many cases, AWS services offer native features you can enable to achieve a secure solution. It's up to you to actually use them. In other cases, you may devise your own solutions to meet compliance and security standards for your specific industry or use case. So that's the shared responsibility model at a high level. I do want you to keep something in mind, though. There is some amount of nuance you should understand as we move through the course regarding the shared responsibility model. Each AWS service is different and serves a different purpose and a different use case. Therefore, the shared responsibility model can vary from service to service as well. This is a good thing as you get to decide how to build your solutions on AWS. When you create an AWS account, you sign up with an email address and you create a password. The email address you sign up with becomes the root user of the AWS account. This root user has unrestricted access to everything in your account in most cases. We will discuss in a later lesson what types of users can be restricted and how to do that. But for now, I want you to understand that when you log into your AWS account using an email address and password, it means you are logging in as the root user. This root user can do whatever they want in the account. It has all of the powers that can be had. And with great power comes great responsibility, or something like that. So, knowing that the root user is all powerful, you should do everything you can do to make sure that no one can gain access to this root user. Let's say there's a nefarious actor of sorts, and they have an evil plan to log into your AWS account with your root user, gaining access to all of the powers and permissions. And they go and delete all of your valuable data and AWS resources. And in their place, they spin up a lovely and expensive cryptocurrency mining operation, leaving you with the bill and none of your data as they walk away with a full crypto wallet. Sounds less than ideal. Well, how can you prevent that from happening? You could, of course, create a hard to crack password, and that will give you some level of security. This, however, is an example of single factor authentication, where all someone needs to do is match the password with the email address, and boom, they're in. We recommend, as a best practice, that right after you create your AWS account, you enable multi factor authentication, or MFA, on the root user. MFA introduces an additional unique piece of information that you need to enter to gain access to the account. There are a variety of devices, virtual or physical, that generate one time passwords that can be integrated with your AWS account for MFA. For example, I personally use a virtual MFA device that is an app on my phone. This app produces a string of numbers for one time use that I type into the console after I log in using my email address and password. Even if someone guessed the password, they cannot gain access to the account without the numbers generated by the virtual MFA device. No matter what type of MFA device that you choose to use, and I will include a link to the supported devices in the readings for you to look into, the most important thing is that you are using MFA on the root user. That way, even if someone, the nefarious actor, cracks your password, they still cannot gain access to your account, all thanks to MFA. On top of enabling MFA for the root user, we strongly recommend that you do not use the root user for your everyday tasks, even the administrative ones. There are really only a few actions that require root user access. Coming up, you'll learn how to create an IAM user and use that to log into your AWS account instead of using the root user. Let's take a look at the application we are going to be building out throughout the course. We've already gone over the design of this application, and what I want to focus on now is access control. There are multiple places on this diagram where we can identify the need for access control and credential management. The first being that we need to manage how users log in and use the employee directory application. We could require that people have a valid credential, like a username and password, to log into the app. That is access management on the application level. Then there is the fact that we know the code running the employee directory application on a virtual machine being hosted by the service Amazon EC2. And that code will need to make API calls to the object storage service Amazon S3 in order to read and write data like images for the employees. Well, here's the thing. Just because both Amazon EC2 and Amazon S3 have existing resources in this account, it doesn't mean that the API calls made from the code running on the EC2 instance to S3 are automatically allowed to be made. In fact, all API calls in AWS must be both signed and authenticated in order to be allowed, no matter if the resources live in the same account or not. The application code running on the Amazon EC2 instance needs access to credentials to make the signed API call to Amazon S3. So that's another place with the need for a credential and access management. Now, let's take this a step further. How are you going to build out this architecture? Well, you'll need access to an AWS account through the use of a login. Your identity within this AWS account will need permissions to be able to do things like create this network, launch the EC2 instances, and create the resources that will host and run the solution in AWS. Yet another place you need credentials. The root user, which you have already learned about in a previous lesson, has these permissions, but you don't want to be using the root user to administer your AWS resources. And let's assume you won't be the only one working on or building out this application. It's more likely that within one AWS account, there would be many people who need access to build and support your solutions. You'll have different groups of people responsible for different parts of the architecture. The people who would write and deploy the code might be software developers, whereas the people who would be responsible for making changes to, say, the network would be a different group of people. You wouldn't and shouldn't give everyone who needs access to the AWS account the root user credentials to log in. You instead would have unique credentials for each person logging in. This is where the service AWS Identity and Access Management comes in. We identified three places where we will need access and credential management. AWS Identity and Access Management, or IAM, can help take care of these two spots on the diagram. AWS IAM manages the login credentials and permissions to the AWS account, and it also can manage the credentials used to sign API calls made to AWS services. IAM would not, however, be responsible for application level access management. The code running on this instance would use separate appropriate mechanisms for authenticating users into the application itself, not IAM. All right, so let's start with the AWS account level. IAM allows you to create users, and each individual person who needs access to your AWS account would have their own unique IAM user. Creating users for everyone who needs access to the account takes care of authentication. Authentication being verifying if someone is who they say they are because they had the proper credentials to log in. Now it's time to introduce authorization. Authorization is this. Let's say you've logged in and you are who you say you are. You've been authenticated. Now you want to create resources and manage AWS resources, like create an Amazon EC2 instance, for example. Sure, you've logged in, but do you have the correct permissions to be able to complete that action? The idea that your permissions control what you can or cannot do is authorization. Are you authorized to launch an EC2 instance? IAM users take care of authentication, and you can take care of authorization by attaching IAM policies to users in order to grant or deny permission to specific actions within an AWS account. Keep in mind, when I say action here, I'm referring to an AWS API call. Everything in AWS is an API call. IAM policies are JSON based documents. Let's take a look at an example. This IAM policy document contains permissions that allow the identity to which it's attached to perform any EC2 related action. The structure of an IAM policy has an effect, which is either allow or deny. An action, which is the AWS API call. In this case, we have EC2 colon star, which includes all EC2 related actions. You can restrict this to be specific API calls. For example, I can restrict this action to be just run instances, and then any user with this policy attached would only be allowed to run EC2 instances, but perform no other EC2 related tasks. IAM lets you get very granular with your permissions in that way. Continuing with this example, we see the resource, which allows you to restrict which AWS resources the actions are allowed to be performed against. You can also include conditions in your policies that can further restrict actions. IAM policies can also be attached to groups. IAM groups are very simply just groupings of IAM users. You can attach a policy to a specific user or a group. When you attach a policy to a group, any users that are a part of that group would inherit the permissions. We recommend that as a best practice, you organize users into groups and assign permissions to groups instead of individual users where possible. This makes it easier to manage when people change job roles or multiple users need permissions applied or revoked. Another best practice to follow is that we recommend when you create your AWS account, you set up MFA for the root user, then create an IAM user with admin permissions. Log out of the root user and then log in with the IAM user that you just created. From there, you can use this user to create the rest of the IAM groups, users, and policies. The reason we suggest you do this is because you cannot apply a policy to the root user, but you can to an IAM user. Now that I've told you about IAM users, groups, and policies, we've addressed this part of access management that we needed for our application. But what about this part? The EC2 instance needs credentials to be able to make the signed API call to S3 for reading and writing employee images. Am I suggesting that you make an IAM user with a username and password for the application running on EC2 to use? No, I am not. This is where role based access comes into the picture. Coming up, we will learn about the temporary access that IAM roles provide and how it can apply to this use case here. All right, so you've learned about IAM users, groups, and policies. Policies can be applied to AWS identities like users and groups to assign permissions. They also, however, can be applied to another AWS identity, IAM roles. An IAM role is an identity that can be assumed by someone or something who needs temporary access to AWS credentials. Let's dive into what I mean when I say AWS credentials. Most AWS API calls that are made must be signed and authenticated, but how does that process work? When you send HTTP requests to AWS, you must sign the request. This signing process happens programmatically and allows AWS to verify your identity when a request is made and run through various security processes to ensure a request is legit. IAM users have associated credentials like an access key ID and secret access key that are used to sign requests. However, with regards to our architecture, the code running on the EC2 instance needs to sign the request sent to S3. I already told you that I don't intend for you to create an IAM user with credentials to be used by this app. So, how will the application gain access to the needed AWS Access Key ID and AWS Secret Access Key to sign the API call? The answer is IAM roles. IAM roles are identities in AWS that, like an IAM user, also have associated AWS credentials used to sign requests. However, IAM users have usernames and passwords as well as static credentials, whereas IAM roles do not have any login credentials like a username and password, and the credentials used to sign requests are programmatically acquired, temporary in nature, and automatically rotated. In our example, the EC2 instance will be assigned an IAM role. This role can then be assumed by the application running on the virtual machine to gain access to its temporary credentials to sign the AWS API calls being made. A role can be assumed by many different identities and they have many use cases. The important thing to know about roles is that the credentials they provide expire and roles are assumed programmatically. To get an idea of this, let's create a role using the AWS console. I'm already logged in and will navigate to the IAM service. Now I want to create the role the EC2 instance is going to use for the employee directory application. Now we will click Roles in the left-hand side and select Create Role. We will then select the trusted entity this role is intended to be used for, and in our case, this will be EC2. Then we will click Next. Now we get to select the permissions assigned to this role. Again, permissions being what actions does this identity have the authority to take. We want this identity to be able to read and write to Amazon S3. So I will search for S3, and you can see there are multiple options here for pre-written policies that I can choose from. I also can write my own custom policy, which would also show up here if I created it ahead of time. I'm going to select S3 full access for the policy. In the real world, you would choose a more restrictive IAM policy for this. But for a proof of concept like this course is intended to provide, we will leave the permissions a bit looser for now. You would come back and change the permissions attached to this role to be more granular if this were ever to make it to a production type environment. Now we also need to add another permission here, and that's for DynamoDB. So I will exit out of the S3 filter and then type in DynamoDB and hit enter. And then we will select the Amazon DynamoDB full access permission. Then we will click next. Then we can give this role a name, which is employee web app role. Then we can scroll down and we can click create role. We can see that this role has now been created successfully. And if we click on the role and scroll down, we can then see that this role has two permissions attached. It's very common for roles to be used for access between AWS services. Just because two resources exist in the same AWS account, it doesn't mean that they can send any API calls to each other. If one AWS service needs to send an API call to another AWS service, it would most likely use role-based access, where the AWS service assumes a role, gains access to temporary credentials, and then sends the API call to the other AWS services who then verifies the request. Another identity that can assume an IAM role to gain access to AWS is external identity providers. For example, let's say you have a business that employs 5,000 technical employees that all need access to AWS accounts. You already have an identity provider system in place that allows these employees to log into their laptops and gain access to various corporate resources. Should you also now go create 5,000 IAM users for these employees to access AWS? Well, that doesn't sound very efficient. You instead can leverage IAM roles to grant access to existing identities from your enterprise user directory. These are known as federated users. AWS assigns a role to a federated user when access is requested through an identity provider. We also have AWS services that can make this process easier, such as AWS IAM Identity Center. These are a couple of examples of role-based access in AWS, and this is just the introduction. Check out the class readings for more information, and don't worry if you don't quite grasp this concept yet, as we will continue using roles in our demos and examples throughout this course. Hello, everyone. In this video, we are going to create the IAM role for our employee directory application. And we will also look at how to create users and look at the different AWS access keys, which are used for programmatic access to AWS APIs. So to start off, let's create the role for our application by selecting roles in the left-hand navigation of the IAM dashboard. And then we will click create role. On this page, we need to select what the trusted entity type is to assume this role. We know that roles allow you to get access to temporary credentials that are used to make calls to AWS API calls. You want to make sure that you're restricting who can assume this role. Not anyone can assume this role, right? So, under the trusted entity type, we have the AWS service. An AWS service, that would be something like an EC2 instance, a Lambda function, other services that are assuming a role to make AWS API calls. You could have an AWS account. This would allow you to allow cross account access to permissions for resources in your account. You also could select a web identity, which would allow for federated users to assume a role. You have a SAML 2.0 federation. So if you have a corporate directory that is on premises that would be using SAML, you could use this as your trusted entity type, or you could create a custom trust policy. We're going to select AWS service for this. And then we're going to select EC2 since our employee directory application will be running on EC2. Next, we can select the next button, and then we're brought to the page to add permissions. This lists out the different permissions policies that are in IAM. And right now, it's pulling back the AWS managed policies that exist in this account by default. And what a managed policy is it is a policy that is created and managed by AWS. And so, what I mean by that is let's go ahead and look at a policy for S3. So if I type in S3 in the search bar and then hit enter, I'm going to expand this Amazon S3 full access policy. And we can see the JSON, which is the permissions for this policy. We can see we have the effect is allow. That's either going to be allow or deny. There's no other option besides allow or deny. And then there's the action, which is going to define what AWS API calls are allowed to be made. So we can see that we have S3 colon star and S3 object lambda colon star. That's a wildcard to determine all API calls are allowed against this service. And then we also have the resource here, which is also set to star. So this would be all S3 resources. This is a very permissive policy. In the real world, you would likely want to change this to allow just the API calls that your application needs, nothing more, and just the resources that you intend to have this policy be related to. So to do that, you would have to create a custom policy. So if I scroll up, you could click on this custom policy button, which would take you to a new page where you could then create your custom policy. For now, we're going to use the AWS managed policies, and I'm going to select the checkbox for Amazon S3 full access. And then I'm also going to type in DynamoDB and exit out of the S3 filter, and then select the Amazon DynamoDB full access policy here as well, because later in the course, we are going to be using DynamoDB as the database for this application. So to prepare the role, I've selected both the S3 full access and DynamoDB full access. Now we'll click next. Then we can give this a name. I'm going to name this employee web app. And then I'm going to scroll down. We can view the trusted entities here. So this is our trust policy. We're allowing the API call STS assume role. And who's allowed to assume this role? ec2.amazonaws.com. So an EC2 instance is going to be allowed to assume this role only. All right, so now I can scroll down and then click create role. Once your role is created, you can then click on the role, which will bring you to the page where you can see the information about this role, such as the ARN, the Amazon resource name. And you can also scroll down. You can view the permissions attached. You could add new permissions if you want to. You can simulate the permissions. You can view the trust relationships. You can also view any tags associated with this, which are key value pairs. So this is where you can get all of the information about your role and where you can manage your role. So next, what I want to do is create a user. So I'm going to click on users in the left-hand navigation. Then I'm going to click add users and let's give this user a name. Let's say it's EC2 admin. And then I want to click the checkbox for enabling console access. So what that means is I want to allow this user to be able to sign in to the AWS Management Console. So note by default, this was unchecked, meaning that just because you create a user doesn't mean they have access to the console. I'm going to go ahead and check this. And then I'm going to allow an auto-generated password to be created. And then I want to leave the checkbox checked for users to create a password at the next sign in. So this will allow them to change their password once they log in for the first time. Now we'll click next. And next, what I want to do is I'm going to add the users to a group. We currently don't have any groups, so I'm going to go ahead and click create group. And then what I want to do is add a group name. Let's say this is EC2 admins. And then I want to attach a policy to this group because we know that it's a best practice to attach policies to groups, not to users directly. So I'm going to select the Amazon EC2 full access policy, and then I'm going to scroll down and click create user group. And now I can select this user group to add this user into, and then I can click next. And then we can scroll down. We can see the permissions that this one user currently has. It will be inheriting the permissions from the EC2 admins group. And then it also has directly attached to it the IAM user change password permission, which will allow this user to change their password. So now we can click create user. And now we can go ahead and click return to users list. We didn't download the password for this. That's fine. I don't intend to actually use this user. It's just for demonstration purposes. So we'll click continue. And now if I click on this user, what I want to do next is click on the security credentials tab. And if we scroll down, you can see that we have this panel here called access keys. Access keys are going to allow your users to make programmatic calls to AWS using things like the AWS command line, the AWS software development kits, where maybe they're developing locally on their laptop and they need their code to be able to reach out to AWS. So I'm going to go ahead and create an access key here. And then I want to use this for the command line. And then I'm going to go ahead and click the checkbox for I understand the above recommendation. What this is saying is it's saying, hey, there's another service in the browser that you could use to use the AWS CLI called AWS Cloud Shell. We're going to go ahead and create the access keys anyways. I'm going to select this checkbox and then click next. And then I'm going to click next again and click the create access key. All right, so here you can see we have our access key here, and then we have our secret access key, which is not being shown currently on this page, but you could click show and then copy it, and you would use this access key and secret access key to be able to configure your command line locally. Now I'll click done and then click continue. So now for a little bit of cleanup, I'm going to select actions and then I'm going to click deactivate and then deactivate. And then I will click actions and then delete. And then we can copy and paste the access key ID here and then click delete. All right, that's it for this video. Hopefully you know a little bit more about roles and users. All right, you've learned some AWS vocabulary, some of the concepts behind cloud computing, as well as some of the specifics around cloud identity and access management. As a refresher, let's take a look at the architecture diagram we'll be building out. You'll remember that it's fairly complicated at a glance. There are many different services working together to host this solution, and to get this entire thing built out this way will take some time and understanding. You'll get the opportunity to see how each piece is built throughout the upcoming lessons. What I want to do now is show you how we are going to host our employee directory application using a service called Amazon EC2, which has been mentioned in previous videos. I find that the best way for me to explain to you how these services work is to show you how they work. So, what we are going to do is we are going to call Ceph in here to launch an Amazon EC2 instance and host the employee directory application using the defaults provided by AWS. AWS provides you with something called a default VPC, which is a private network for your AWS resources. Every EC2 instance you launch using AWS must live inside of a network. So, in order to complete this demo with the limited amount of information that we have shown you about AWS services, we will be using the default network provided by AWS, and we will accept most of the default values for launching an EC2 instance. Let's bring Seth in for some help with this one. Hey, Seth.
Hey, Morgan. Is it time to launch our first EC2 instance?
It is. We'll be using the default VPC to launch this first instance, and we will configure the bare minimum to get our application up and running. Sound good?
Yep, I got it. Let's get started. I'm already in the EC2 management console, and I will navigate to the service Amazon EC2. As Morgan already mentioned, Amazon EC2 is a compute service that allows you to host virtual machines. You'll learn a lot about this topic coming up soon, but for now, we are going to simply create an EC2 instance to try and help you wrap your mind around using AWS services on demand. From here, we'll launch a new EC2 instance. An instance is just what we call one single virtual machine. Now we have to select the configurations for this EC2 instance. You will go over these configurations in detail later. We can give this instance a name. I'll call it Employee Web App, and then we will select the free tier eligible options using a Linux AMI or Amazon machine image. And then scrolling down to the next section, we will select the free tier eligible T2 micro for the instance type. Next, we normally need to select a key pair. This would be used to SSH into the instance. But we won't need to do this, so I'm going to select proceed without. A key pair and continue scrolling to the network settings. Here, we will select the network. So looking at network settings, we will click Edit. Then we can select the VPC and subnet for this instance. And as we discussed earlier, we will use the default VPC and leave the subnet at no preference. The default VPC has configurations in place that make this experimentation process a lot easier when you're first getting started with AWS. Again, we will define all of these things later. Continuing on with network settings, we will create a new security group, which is an instance level firewall that will allow HTTP and HTTPS traffic in to reach the instance. So we will add inbound rules for traffic, which continuing on with network settings, we will create a new security group, which is an instance level firewall that will allow HTTP and HTTPS traffic in to reach the instance. So we will add inbound rules for both of those. Now we will scroll down and expand advanced details. So we will add inbound rules for both of those. Now we will scroll down and expand advanced details. We will accept most of the defaults here except the IAM instance profile and user data, which we will provide a value for. For the IAM instance profile, we will use the IAM role that will be used by the application, though this won't come into play until later when we have our S3 bucket created. But for now, let's click the dropdown and select that IAM role. Now, scrolling down to the user data, this is a script that is going to run when the instance boots up. Let's go ahead and paste in our user data script. This script will download the source code for the app, start the web server, and kick off the application code so it's ready to start handling requests. While you could have launched the instance, then connected to it via SSH, configured and started your application manually, we have decided to use a script to automate this process on launch. All right, now we can click Launch Instance. It can take a few minutes for the instance to boot up, so let's wait for that. And now it's up and running. To access the instance, copy the IP address from the details listed below, paste it into a new browser tab, and there you go. It's up and ready to go. Morgan, what do you think?
That looked great. It's exactly what I would expect at this point because there is no data being served from a database. So I expect to see just a home page with no info. So that's great. Thank you, Seth, for walking us through that. In upcoming lessons, we will discuss the specifics of not only EC2, but also networking on AWS, and you'll understand how everything we just kind of glossed over actually works. So stay tuned. All right, you've learned some AWS vocabulary, some of the concepts behind cloud computing, as well as some of the specifics around cloud identity and access management. As a refresher, let's take a look at the architecture diagram we'll be building out. You'll remember that it's fairly complicated at a glance. There are many different services working together to host this solution, and to get this entire thing built out this way will take some time and understanding. You'll get the opportunity to see how each piece is built throughout the upcoming lessons. What I want to do now is show you how we are going to host our employee directory application using a service called Amazon EC2, which has been mentioned in previous videos. I find that the best way for me to explain to you how these services work is to show you how they work. So, what we are going to do is we are going to call Ceph in here to launch an Amazon EC2 instance and host the employee directory application using the defaults provided by AWS. AWS provides you with something called a default VPC, which is a private network for your AWS resources. Every EC2 instance you launch using AWS must live inside of a network. So, in order to complete this demo with the limited amount of information that we have shown you about AWS services, we will be using the default network provided by AWS, and we will accept most of the default values for launching an EC2 instance. Let's bring Seth in for some help with this one. Hey, Seth.
Hey, Morgan. Is it time to launch our first EC2 instance?
It is. We'll be using the default VPC to launch this first instance, and we will configure the bare minimum to get our application up and running. Sound good?
Yep, I got it. Let's get started. I'm already in the EC2 management console, and I will navigate to the service Amazon EC2. As Morgan already mentioned, Amazon EC2 is a compute service that allows you to host virtual machines. You'll learn a lot about this topic coming up soon, but for now, we are going to simply create an EC2 instance to try and help you wrap your mind around using AWS services on demand. From here, we'll launch a new EC2 instance. An instance is just what we call one single virtual machine. Now we have to select the configurations for this EC2 instance. You will go over these configurations in detail later. We can give this instance a name. I'll call it Employee Web App, and then we will select the free tier eligible options using a Linux AMI or Amazon machine image. And then scrolling down to the next section, we will select the free tier eligible T2 micro for the instance type. Next, we normally need to select a key pair. This would be used to SSH into the instance. But we won't need to do this, so I'm going to select Proceed without a key pair and continue scrolling to the network settings. Here, we will select the network. So looking at network settings, we will click Edit. Then we can select the VPC and subnet for this instance. And as we discussed earlier, we will use the default VPC and leave the subnet at no preference. The default VPC has configurations in place that make this experimentation process a lot easier when you're first getting started with AWS. Again, we will define all of these things later. Continuing on with network settings, we will create a new security group, which is an instance level firewall that will allow HTTP and HTTPS traffic in to reach the instance. So we will add inbound rules for both of those. Now we will scroll down and expand advanced details. We will accept most of the defaults here except the IAM instance profile and user data, which we will provide a value for. For the IAM instance profile, we will use the IAM role that will be used by the application, though this won't come into play until later when we have our S3 bucket created. But for now, let's click the dropdown and select that IAM role. Now, scrolling down to the user data, this is a script that is going to run when the instance boots up. Let's go ahead and paste in our user data script. This script will download the source code for the app, start the web server, and kick off the application code so it's ready to start handling requests. While you could have launched the instance, then connected to it via SSH, configured and started your application manually, we have decided to use a script to automate this process on launch. All right, now we can click Launch Instance. It can take a few minutes for the instance to boot up, so let's wait for that. And now it's up and running. To access the instance, copy the IP address from the details listed below, paste it into a new browser tab, and there you go. It's up and ready to go. Morgan, what do you think?
That looked great. It's exactly what I would expect at this point because there is no data being served from a database. So I expect to see just a home page with no info. So that's great. Thank you, Seth, for walking us through that. In upcoming lessons, we will discuss the specifics of not only EC2, but also networking on AWS, and you'll understand how everything we just kind of glossed over actually works. So stay tuned.